Do you know derivative? Have you ever wondered how fast something is changing? Right now, imagine you're on a road trip and your car's dashboard shows your speed. That speed tells you how fast your distance is changing over time right now. If you're going 60 miles per hour, that means at this instant, you're covering 60 miles each hour. In this case, distance equals the function. Speed equals the derivative of a distance. The derivative is just like how speed tells you how fast something is changing at the exact moment. In short, a derivative tells you how fast something is changing right now, like a speedometer for any kind of change, not just any motion.
Geometric interpretation. Secant. Let's start with 2 points on the curve. When we connect them with a straight line, we get something called a secant line. The slope of the secant line tells us the average rate of change between the 2 points, like how far it traveled over a time interval. Like as shown on the screen, the change in y over the change in x. Now, watch what happens when we slide the 2 points closer and closer together. The secant line starts to become a better and better approximation of the curve's behavior at just 1 point. And when those 2 points come together, the secant line becomes a tangent line. This tangent line represents the curve's direction at that exact point, its instantaneous rate of change. The slope of the tangent line is what we call a derivative. It just tells us how steep the curve is wherever it's rising, falling, or flat right at that point. Just like your car's speedometer shows how fast you're going at this very moment, the derivative tells us how fast the function is changing right now. So to sum up, a secant line gives us an average rate of change, while a tangent line gives us the instantaneous rate, and the derivative is the slope of that tangent, a snapshot of change in motion. Derivatives are everywhere in physics, economics, biology, and beyond. Understanding them starts with just this: a curve, a line, and a question. How fast is it changing right now? The power rule. If you have a function like x to the power of n, just bring the power down in front and subtract 1 from the exponent. As seen on the screen, d over dx and then x to the power of n is equal to nx to the power of n minus 1. Say you're looking at the curve x squared. The shape tells us the slope is changing, getting steeper as x increases. The derivative of the slope of the tangent line tells us how fast x squared is growing. Turns out it's 2x. And that leaves the power rule. Start with 2x. Bring the 2 down. Minus 1. From x squared, it becomes 2x. The graph is rising faster as x increases. Now that we understand the power rule, let's try a few examples together. You'll see how easy this becomes. F of x is equal to x cubed. Now let's try to solve it. Bring the 3 down, subtract 1 from the power. From 3x cubed minus 1 to 3x squared. That's it. That's the slope of x cubed. At any point, x is 3x squared. Now, let's try another one. F of x is equal to x to the power of 7. X to the power of 7 is equal to x to the power of 7 minus 1. equals 7x to the power of 6. Easy, right? Well, let's try one more. F of x is equal to 1 over x. We will write it first using negative exponents. So f of x is equal to x to the power of negative 1. Now, apply the rule. D over dx with x to the power of negative 1 equals negative 1 x to the power of negative 2 is equal to negative 1 over x squared. And yeah, that's how the power rule works. And in this problem, power rule still works. To sum up, what you need to know here is positive powers grow faster as x increases. Negative powers get smaller or more negative. Roots grow slowly. Their derivatives are small numbers. To remind you, the power rule is the backbone of basic calculus. If you can master this, you can differentiate tons of functions in seconds. Next up, you'll learn how to handle more complex expressions like sums, products, chains, and beyond. As seen on screen, again, d over dx to the power of x to the power of n is equal to nx to the power of n minus 1.
Another basic rule. Constant multiple rules. This rule states that when you multiply a function by a constant, the derivative of simply that constant times the derivative of the function. For example, the derivative of 5x squared is 5 times derivative of x squared. Since the derivative of x squared is 2x, we get 10x. Sum and difference rule. It explains that if you have the sum or difference of two functions, you may simply add or subtract their derivatives. Let's try this. What's the derivative of x squared plus 3x? Easy. Take the derivative of each part. The derivative of x squared is 2x, and the derivative of 3x is 3. So, the final answer is 2x plus 3. And here's a subtraction example. The derivative of x cubed minus 2x is 3x squared minus 2. Simple. Constant rule. The derivative of a constant number is 0. Why? Because the constants do not change and derivatives quantify change. So whether it is 7, negative 42, or 1000, the derivative are always 0. Product and quotient rules. Let's move on to more advanced and derivative rules that help us deal with more complex functions. The product rule and the quotient rule. When you're taking the derivative of a product of two functions like f of x equals u of x times v of x, you can't just take the derivative of each and multiply them. That's a common mistake. Instead, we use the product rule, which states this means take the derivative of the first function, multiply it by the second, then add the first function times the derivative of the second. Example number 1. Step 1. Derivative of x squared is 2x. Step 2. Derivative of cosine x is cosine x. Now, apply the rule. You kept one function untouched while differentiating the other, then you switched. Quotient rule. Now look at the division. When one function is divided by another, you use the quotient rule. A popular way to remember it is low d high minus d low over low low. Let's break that down with an example.
Example number 2. Step 1. Derivative of the number x is 1. Step 2. Derivative of the denominator x squared plus 1 is 2x. Now plug into the formula. Tip: be extra careful with signs that parentheses here. It's easy to make small mistakes.
These rules form the foundation for understanding motion, growth, and change in real-world contexts, like velocity in physics, cost functions in business, or population models in biology.